Hello students, in this video we'll introduce the idea of a Schwarz Christoffel mapping which maps the upper half space onto a polygon. So let's recall, if C is a curve in C and W is equal to f of Z is a transformation, taking C to gamma, then at a particular point Z0, we let t hat be the tangent vector to C, tau hat the tangent vector to gamma, and then, so that, and here's the important part, so that what? This is the basis of the Schwarz Christoffel idea. The argument of tau hat, is the argument of f prime of Z0 plus the argument of t hat plus the argument of t hat. So in particular, what this formula tells me is that if the curve C is the real axis, then the argument of t hat is 0, right? So arg t hat equals 0 if C is just the real axis, the real line, okay? And that's what we're going to assume. So we're going to assume that C is the real line. Excellent. Then on any stretch, on any interval, I, a subset of R, for which the argument of f prime of x is constant on x in I. That means what? That means that tau hat is constant argument, implies argument of tau is constant C1 as well, right? Now what does that mean? The argument of tau hat being constant means that means the curve gamma is also what? Is also a straight line. Beautiful, because the tangent vector is only going to be constant if you're what? If you're on a straight line, right? Good. Okay, so that proves the following. It proves that if I carefully select my f prime for my transformation, so the argument is constant on different intervals, I'll be able to map to a polygon. That's the idea of Schwarz Christoffel. Okay, good. And so now here is your Schwarz Christoffel transformation. So this is our Schwarz Christoffel. So here's the idea. We're going to let x1, x2, xn minus 1 be points on the real line. And you can order them so they're increasing. Fine. And then k1, kn minus 1 numbers such that real numbers with the ki, these numbers ki are between -1 and 1. And I want the sum of them, I goes from 1 to n minus 1 of ki to be at least 1. Okay? I want it to be 2 actually, but at least 1, because I want to allow for some degenerate polygons in my situations, okay? So I need those two conditions, okay? Now, here's the mapping. I'm going to give you the derivative, right? And we're going to see why the derivative works, right? So f prime of z is just some constant a, and then z minus x1 to the negative k1. Z minus x2 to the negative k2, all the way down to z minus xn minus 1 to the negative kn minus 1. Beautiful, okay? Now, why is this going to work, okay? Let's think about what's going to happen over here. What's the argument of f prime of z? Argument of f prime, let's put just an arbitrary x in there, like x on the real line. It's going to be the argument of a minus k1, the argument of x minus x1, all the way down minus the argument k, of course, right? Kn minus 1, the argument of x minus xn minus 1. Beautiful, okay? Let's think about what's going to happen over here in this formula. Okay, I'm going to draw it out. I'm going to draw it out in an interval, and we're going to figure out what happens. Okay, here's the point: x1, x2, x3, xn minus 1. Okay, there's the real line. What happens to the argument when you jump from these points over here to these points over here? When you hit x1 and go over x1, let's think about what happens. If you're between x1 and x2, what's this first argument over here? If you're bigger than x1, then x minus x1 is a positive number. There's no argument there. So this one goes what? This term goes away. That's gone, right? Because if I plug in like x1 plus epsilon, then this is just the argument of epsilon, and that's just a real number, right? With zero argument. So over here, as I go over x1, the argument jumps by k1 pi. As I go over to x2, what happens? I jump by what? k2 pi. As I jump over x3, what happens? I jump by k3 pi. As I jump over xn minus 1, what happens? I go to kn minus 1 pi. So what's happening as I hit these points on the real line is at these points on the real line, my argument jumps. So my angle changes. Oh, an angle changes represents a what? A bend in a polygon, right? Neat. Okay? And remember, and it's constant, right? In between those 2 points, everything else is static. It's not changing at all because you have to get to x2 before you jump again, right? So in other words, you're going all the way from the points over here, we have this huge argument, to the points over here where all those are gone, and over here you're just the argument of a, right? Just the argument of a. Good, okay? Excellent, okay? And so now what does this correspond to? What this is going to look like is the following. This is going to look like if x1 goes to w1, here's w1. And then we go to w2. That's w2 right there. And then what happens as we go from x1 to x2? Well, as we go from w2 to w3, what's going to happen over here? Then you can go over here to w3, for example. And then this number over here is how much you changed at w2, because you got to w2 and you went over it. So this change over here is exactly what? Is exactly k2 pi. If I went to w4 over here, then this angle over here would be what? That would be k3 pi, et cetera, et cetera, et cetera, et cetera, right? Beautiful, right? So I'm sort of forming these angles. Now, of course, what can I say about this? I know that this angle over here, this interior angle, let's figure out the interior angle, because we want to do those interior angles too, right? What's this interior angle over here? Well, this is going to be 1 minus k2 times pi, right? So that interior angle theta is this, right? So this is your interior angle. Let's call that theta 2, right? That's your interior angle theta 2. And of course, you can solve for theta 2 in this formula, right? So therefore what? Therefore, you can say that k2, so if we divide by pi and subtract, you get that 1 minus theta 2 over pi is equal to k2, right? So that's the formula. And in general, right? The general formula is 1 minus theta I over pi is equal to ki. That's the relationship between the thetas, which are the interior angles of the polygon, and the k times pi, which are the exterior angles of the polygon. Great. Okay, now what's the last glitch of this? There's not really a glitch per se, but I'm actually allowing infinity to play a role in this, right? And so I'm going to claim that what f of infinity, so f of infinity is going to be Wn, okay? So f of infinity is going to be Wn, and that's why I need this condition over here. This condition guarantees that f of infinity exists, okay? Good. Prove it. It's pretty simple, right? It's just basically an integrability condition, okay? Excellent. Okay, so f of infinity is Wn, and so what do we need about the external angle? If that's Wn, I need that external angle over there at Wn to be what? Let k and pi be the external angle at Wn, which is f of infinity. Okay? Then for the polygon to be closed, the exterior angles need to be 2 pi, right? In other words, k n pi has to be 2 pi minus k1 plus plus kn minus 1 times pi. And therefore, what's our conclusion? Our conclusion, therefore, is that to be a closed polygon, I need k1 plus k2 all the way down to kn to be equal to 2, right? I need that to be equal to 2. And if this condition is true, I have some shot at it, right? So once I specify all of the first n minus 1 exterior angles, specifying the last exterior angle at the point in infinity is going to close up the polygon for me. Now what that tells you is that this Wn over here, so as I go from say for example I went from W4 to Wn, the last one. That corresponds to what? That corresponds to this branch going to infinity, right? What about these branches over here, from infinity to W1? How do I go from infinity to W1? Oh, going from infinity to W1, like that, is going to correspond to what? Is going to correspond to this branch over here, right? So the point at infinity is hard to get to, right? In some sense, the polygon, in some sense, analytically, never closes, right? We have to go all the way to infinity. And look at what's in the Riemann sphere. When we go there, when we hit infinity, we actually get that closed point on the polygon. Beautiful, right? And so for most applications, it's important to understand that going this way from the last vertex over here, the Wn minus 1 to infinity, goes from there to there, right? And then going back, you have to traverse along this first component from negative infinity all the way up to x1. So remember, we're using like the circularity, right, or the closeness of the Riemann sphere to actually close off the polygon, right? So in other words, what we're going to see in further videos is we're going to see that once, if I want to specify like a triangle or a square or a rectangle or a pentagon, hexagon, heptagon, whatever you want, right, or some strip, degenerate ones, what you're going to need to do is you're going to need to carefully select these k1 through kn minus 1 through kn, and also be very diligent about the choice of the x1 through xn so that you can put these integrals, which are, generally speaking, elliptic integrals which you can't explicitly evaluate, you need to put them into a form where there's lots of symmetry so you can exploit the symmetry of the problem, right? So I really want to not just haphazardly put these points x1 through xn minus 1 on the real axis. That won't help me very much with the integral I get. And I'm just going to say it's this constant integral, which we can't evaluate even with residues, right? And so I need to very carefully specify that using the symmetry of the x1 through xn, how I can actually plot these, plotting the displacement and choosing them carefully to get the sort of the classical figures that I want to see. Thank you very much.